an interesting, it's an interesting initiative to make this kind of courses, with kind of event, especially with this. As with pandemic, we look for different ways, to live. So this was a southern hemisphere is certainly an interesting geometrical concept. I think this is. So all right. So I'm to give a course on this spontaneous stochastic solutions. It will be 3 lectures. I don't know how long will be each lecture. Probably I will try not to be too long. And so that the goal will be to present the topic in general of this spontaneous stochastic phenomenon. And I will try to do it from different perspectives. Certainly, analysis is one of the very big issues here. Though I will be not teaching too much of the methods, because there is it's more the demand for analysis than there is a. It's more that there is a big need for analysis in this area rather than there is analysis already ready. So I will be talking about the concepts, how we approach these spontaneous stochastic solutions, and what's necessary, what happens, and how we understand it. And certainly this is a rather multidisciplinary topic. So I will jump from time to time from analysis. There will be dynamical systems, differential equations, partial differential equations, ordinary differential equations, and there are a lot of applications. So there's a lot of there is big demand for the application, though still we don't understand much in this subject. Okay, so. Okay, so the this is just small picture. So I don't know how many people here do not never saw IMPA. So IMPA is Institute of Pure and Applied Mathematics. Here it's like how it looks like. It's in the middle of the forest. I think most of the people here know it. So this is the entrance. And this is some relatively old picture of our group in the laboratory of fluid dynamics. So this is laboratory of fluid dynamics, where most people sit, because we need we needed to discuss the things by sitting together. And here, one floor below is this computer center, data center. So there is this different clusters, cooling machines. So so one floor below is this computational facilities. One floor above is the human brains, and then people work and think. So part of our group work with the turbulence, and this is one of the areas where the spontaneous stochastic solutions make sense. But origin is much more deeper into the analysis. So this is a plan. So today I'm not going to come to the. I will start with general historical remarks. Then we'll talk about rather basic things about uniqueness and non-uniqueness of solutions. And then from this, we can come to the question of singularities. Singularities, or in some cases, it's called blow-up. So this kind of formation of singularities as a form of source of non-uniqueness, which eventually may lead to the spontaneous stochasticity. And some of the techniques that allow to study these singularities for times before they occur. So the spontaneous stochasticity will correspond to the time after. But today we will discuss just what happens before. So historical remarks. So first, surprisingly, this topic goes to the same, goes back, can be traced back in a mathematical, I would say, formulation, though not a rigorous mathematical formulation, but anyway, in mathematical formulation, it goes back to the same person from whom the theory of chaos emerged, so the Edward Lorenz. So Edward Lorenz, who in fact was working on weather prediction, so he was essentially his main interest were analysis of the fluid dynamics, so the weather prediction. So he had these three separate papers. So the first two of them directly correspond to what we know nowadays as the deterministic chaos. So one of the papers introduces the Lorenz system. So this is three coupled ordinary differential equations, which are obtained from some very rough approximation of fluid dynamical instability. So in these two papers, this system is introduced and also studied essentially numerically. So Lorenz discovered that if you take this relatively simple system, just three ordinary differential equations, and just you evolve it long in time, it doesn't go to any simple solution. So it's not becoming fixed point, not becoming periodic solution or something that we can simply understand, but rather it is tracing what he called strange attractor. So it's strange, well, strange. Now it's not so strange. So now many people prefer to call it chaotic attractor. So, but at that time it was very strange because it didn't look like something usual. It doesn't look like this today as well. So anyway, it's a fractal set. So the solution comes to the fractal set, close to the fractal set, and goes along the fractal set all the time. So this is one of the properties of the solution. Another property of the solution is that if you consider two different, so is that though it's attracted to this set, at the same time, individual solutions are extremely unstable. So if you consider two very close initial conditions, you can show that the separation between two initial conditions grows exponentially. It grows exponentially. It's fast, which means that at some reasonable time, at long but not that long. So at some reasonable time, even if you introduce a very small error into your data, you will forget. You will go to a completely different solution. So solutions forget very fast what are the initial conditions. Okay, but they know where they are. So they are near this attractor. So this was the first two papers, which of course are now extremely famous, and the whole theory of dynamical systems in a large part of the theory emerged from these two works. So now, just to say that about this particular system, the Lorenz system, we know quite a lot rigorously. So there are a lot of mathematical results which describe what happens and about structural stability and all these kind of questions in a rigorous way. And this is actually rather recent results. I would say that big part of the results which are rigorous mathematically, they were obtained in just last few decades. So despite they were started, you can see, and 1963. So real mathematical, rigorous mathematical proofs, they came out 40 years after. But at the same time, there is another paper which was which is also known, not as much as the previous, but rather known. So it's called Predictability of a Flow which possesses many scales of motion. So the difference here is that it's not a single scale of motion that was, or small number of scale of motions that's considered in the Lorenz system, but many scales of motion in the sense that many, very many, in some asymptotic sense that there is infinite dimensional system. This is an interesting paper. And the interesting part can be read directly from its abstract, from even not from abstract, from the beginning of this abstract. And this beginning of the abstract is exactly gives you an idea. One of the sides of what we understand as spontaneous stochasticity. So let's read it. So it is proposed that certain formally deterministic fluid systems, so formally deterministic system, which possesses many scales of motion, are observationally indistinguishable from indeterministic systems. Specifically, the two states of the system differing initially by small observational error will evolve into two states differing as greatly as randomly chosen states of the system within a finite time interval. And this time interval cannot be lengthened by reducing the amplitude of the initial error. Okay, so it's a long sentence, so now let's just try to understand it. So it can be understood by opposing what is written to what we understand now as a chaos. So as I already said, the deterministic chaos, which is not the situation that is described by Lorenz in the third paper, in the deterministic chaos, we have the error, like uncertainty in the system. It initially grows exponentially in time. So there is this Lyapunov exponent, lambda. It's positive. So if you have any initial error, it will, after time t, it will be multiplied by exponent lambda t. This exponential growth eventually destroys the predictability. It destroys predictability, but at the same time, formally, system is deterministic, because if you want to know the solution at some time t, and you fix this time t, so you want to know the solution after 1 hour, then you can just have a small error enough so that this error at time t is also small enough. So in that sense, if you have, let's say, very good facilities like computer measurements and so on, you can predict the position of your system at finite time as good as you want. So this is what is deterministic. So the solution, there is unique actually answer for at every time if you know exactly the initial state and you know exactly the equation, and if you are able to solve it. Okay. So the spontaneous stochastic solutions are different, and you can see, for example, if you model if the error, and actually this is the correct expression, which was also anticipated by Lorenz. So if the error is, instead of growing exponentially, it grows as a power law. So power law is a nice is an interesting function. So from one side, we kind of used to have power law to see power law as being something slower than exponential. But power law is slower than exponential at large times. It's completely opposite at small times, because if you can, you see the power law, if you started from initial time t0, it doesn't need any error to grow up. So error grows up to finite time to size 1 at time 1. for this expression. And it doesn't matter what was the initial error. So it doesn't matter how you measure it initially, it will be, you will forget the initial condition. So this is the kind of an image. So we should come to this to see how this comes from equations. And you can see that this is very different from chaos because essentially initial error doesn't matter. So in this kind of system that's suggested by Lorenz, the error will grow independently on intrinsic accuracy of your original system. So there is an interesting story behind all this discussion. Is this rather famous saying that the question about the chaos, that does the flap of the butterfly wings in Brazil set off a tornado in Texas? And this is very close to true, in fact. So the flap of very small uncertainty or very small change in initial condition that may occur very far away, so like in Brazil, may completely change the dynamics of the atmosphere, like the tornado in another part of the world. And there are actually now there are direct indications that this is true. And to what phenomena it should be, this saying should be linked. So interestingly, in the whole popular and scientific popular literature, it's linked to chaos. So the butterfly with the wings in Brazil set off tornado in Texas because of deterministic chaos, and because deterministic chaos has this sensitivity to initial conditions. So you change the initial conditions slightly, and this very small change grows exponentially. So at the end, it will lead to a very different solution. So and this is misunderstanding, because Lorenz himself, it was attributed this thing to this second type of solution, to the type of solutions where the error is growing as power law of time. Because at this kind, the error grows, doesn't matter how small is the initial perturbation is. So whether it is butterfly, or in some other places it's seagull, or even some small molecular motion. So it's just different motion of one molecular can completely change the solution at large times, just because a very small error is enough to change the solution a lot, and how much the solution will change doesn't depend on how small was this initial change. So this is kind of very counterintuitive idea that we'll try to follow. Okay. So this is historical, and now let's go to analysis. So first of all, when we say that there's this saying, so the solutions will differ at finite time independently how small is the initial error, mathematically it's immediately signals that there must be non-unique solutions. So this situation happens under conditions when the solutions of the system are non-unique, and this is usually considered to be a bad situation in analysis. So the message of this spontaneous stochastic of this theory of spontaneous stochastic solution is that actually it's quite physical situation. It's very physical situation. There are many situations in real nature when the system should be described by the system with singularities, and these singularities lead to non-uniqueness. So spontaneous stochastic solution is one of the types of solutions that comes from this non-uniqueness. Okay, so let's just go very back to the basics So first, I will recall you the Picard Theorem. So I'm not giving precise formulations, but idea is all here. So the Picard Theorem is about this system of ordinary differential equations. So X is a vector, but X can be also a point in the Banach space or some more, so you can use more general constructions, but usually in our basic course, X is a vector, and you have initial condition. So the theorem tells that if F is Lipschitz continuous, for example, continuously differentiable, then there exists a unique solution locally in time. So Lipschitz continuity is a crucial component here. So Lipschitz continuity tells that there, at every point there exists, there exists a constant such that for any two real points, the difference of the function is smaller than the difference of the points multiplied by this constant. So this is a picture. So the function f should be some function such that at putting this angle at whatever point of this curve, the function will be always inside this green zone. So it may have some angles, maybe some. It does not need actually to be everywhere differentiable, but at this, it cannot be too bad. Yeah? So, and vice versa, if you want to have non-unique solutions, that the function should be quite rough. So it should change much bigger than this angle. So it should always try to enter in this white region. Okay. And whenever you have this function, you may expect non-uniqueness, and let's see how it occurs just in an explicit example. So this is a very simple example. It's an example of the type that you always have in a graded course, undergraduate course. So this is a one-dimensional differential equation, x dot equal fx, and we take this function which is cubic root of the modulus of x. So this is a graph, and you see that the function is non-differentiable at 0. It's also non-Lipschitz at 0, because at 0 you cannot write any angle such that function will enter. So you see that the function is non-Lipschitz. And this means that in principle, you may expect non-uniqueness coming from this point, from 0. And this is indeed true. So you have, for any initial conditions, which is negative. Yeah, so let's consider initial condition here at the -1. So if you start at -1x, you always have non-unique solutions in the following sense. So first, as long as your negative solution is unique, because you're going along the smooth part of the right-hand side of the function f, until you hit 0, and whatever point you start at in negative x, you will enter 0 at finite time. So finite time you enter 0. So what happens after you enter 0? After you enter 0, you have two ways to go. So the one way is symmetrically. So you can symmetrically just continue, because system is symmetric. No? So you can just take the same path that you entered, but flip it, and it will give you a solution which is written here. So it's t in the power 3/2. Yeah, so t power 3/2 is a coefficient. It's a solution which is leaves you, so that way you leave the singular point to the side of positive x. But there is another solution, because at 0 f is 0, so you just can stay at 0. So this is a red point. So the red curve is a solution, blue curve is a solution. And then there is a theorem that tells that if there are two solutions, then there are infinitely many solutions. So this is also indeed the case here. So there are infinitely many solutions, and you can just construct them by putting together this blue curve and red curve. So how you do it, at for some arbitrary time, you stay exactly at the origin, and then you, instead of gluing this curve to the zero, you attach this curve to this point. So you stay at the origin at a certain point, and then start and leave the origin. So all this happens in finite time. And so all this segment of the red curve with the blue, red curve with the blue, are all different solutions, and there are infinitely many of them. To the question, what is the correct solution? What's the correct solution? So this seems to be this actually seems to be a very academic example. So what system may have this kind of right-hand side? But this is not true, because even on the level of such a small, a simple system, it has a quite direct connection to the theory of the turbulent motion. And in fact, the Kolmogorov theory of turbulent motion tells that in the developed turbulent motions, the difference of the velocities at two different points is proportional to the distance between these 2 points in the power 1/3. So if you take turbulent motion, like what you have in a plane, so when you have to buckle the belts, then it's a turbulent motion around, and turbulent motion has a property in its Kolmogorov theory, at least, so it is approximately correct, that the difference of the speeds between every 2 points in a space, the difference of the speeds will be proportional to the distance in the power 1/3. So you already see that this means that the field of the speeds is non-differentiable, so it's non-Lipschitz because of the 1/3. Okay, and in that case, this equation is exactly the equation that you would derive from this law if you want to see how the distance between two particles changes with time. So imagine initially you put two particles and they're very, very close. So distance x. So the speed between them is cubic root of the difference, right? So this formula. So the change of x of distance in time will be proportional to the cubic root. And this is exactly solutions to the system. So there are many different solutions. So there are many different solutions. And the system can choose different solutions. So different solutions can. So the question, what solution you should choose? And this is not only was studied theoretically, but also was studied experimentally. So I have this picture. This is it's not experimental picture, of course, but just to get an idea. So in 1920, in 20s, Richardson, he made a number of experiments. Actually, he was envisioned this kind of rule, and he tried to check it experimentally. So what he was doing, he was taking many balloons, putting them together, and releasing them. So the balloons with helium, I think, or with hydrogen. So they're light, so they go up. So they move up. So this motion up, it's what substitutes time in this case. And all of them are together initially. So they have just kind of, each balloon kind of describes different solution with a slightly different error of initial condition. And then he was measuring how this branch of balloons spreads in time as it goes up. And he was kind of measuring something similar to the solution of this system, which would be that the distance, that the balloons will go in different directions, so they will all go different paths. and the distance between them will grow as power t 3/2, which is exactly power t 3/2 is the distance of this curve. So there is this kind of example, and there are other examples which are interesting in where the singularities are already inside the equations. And one of the most famous examples is an n-body system. So n-body system, if you remember that n-body system is a system of bodies which just move under the action of the gravitational force, and the gravitational force is proportional to 1 over r squared, 1 over distance squared. So if the bodies are very close to each other, the force becomes infinite. So there is certainly breaking of the ellipsis condition. So there is a question of, okay, they hit each other, so how they go, how they split, and or how they split if they come very, very close to each other. So there are many questions, and there is a whole theory about this related to these singularities in any body problem, and n-body problem is a very old problem. So it's already many conjectures were given more than 100 years ago, and surprisingly, the big considerable progress in this problem of n-body system was done just also in last several decades. Okay, and so these were the problems where the non-Lipschitz condition is realized naturally. And now I would like to show that in examples which are more complicated, like partial differential equations, the singularity, they don't need to be already in the system. So before we already had singularity already in the system in the right-hand side. So either the force become infinite or there is some fractional power. So in partial differential equations, everything looks very smooth and very nice, but singularity will appear naturally in a finite time. So the one of the most probably the charismatic examples is this Burger's equation. So this is inviscid Burger's equation originating from the gas dynamics, but it's a very standard example for the course of partial differential equations. So this is one of the simplest non-linear partial differential equations, which we can completely solve. So we can completely solve this equation. And what we know is that if you consider initial time, so you see this graph, it shows x coordinate. So this is this equation for where u is a function of x, which is just horizontal coordinate, and time. So there is one space dimension, one time. U is a function of both, and u must satisfy this equation. So we're interested in the solution. So in the solution, usually we're interested in the initial value problem. So assuming that u is given at initial time. So u is given at time 0. So at all points of the x coordinate. So if you remember the course, so what you do, you take every point x, then you take the value of u, initial value of u at this point, and then you draw this line. Yeah? So the line with the inclination u0 from this point. Poof. And it's rather easy to see that along this line, the derivative of u, so the derivative of this equation implied that derivative of u along this line is 0, which means that u doesn't change. So which means that along this straight line, the u remains to be u0. So the initial condition, in other words, initial condition at t0 is transported without any change along this fan of lines, and these lines are called characteristic lines. So characteristic just carry the initial value of u0, And looking, so this red characteristic line, they are shown for this initial condition, which is this kind of cosine, no? Sine function. So take this sine function, take it, and this is all characteristics. And you see already clearly that it cannot last forever, because at certain moment characteristics start to intersect. And we already said that each characteristic, it brings its own value, initial value of u0. So at the moment of when characteristics intersect, solution is not determined by this method. So something happens. And what happens, you can see here. So this will be movie. So you see that, so what happens with time is that at the section where the function goes down, it becomes steeper and steeper. You see, it becomes steeper and steeper until the moment where the first characteristic intersect. Until the moment when the first characteristic intersect. And here we stop. So this is where we stop, because we cannot continue solution behind this point. So there is infinite derivative in this point infinite. So whenever derivative of this point infinite, already from a very general point of view, this equation cannot be continued because it's not anymore Lipschitz continuous at this point. So the norm, essentially norms, usual norms under, with respect to which we control this equation, they become infinite. And this is very typical situation in a lot of different partial differential equations, where the partial differential equation originally, it doesn't look to be singular. There is no any singularity explicitly introduced into the equations, but it's formed in finite time by the solution. And there are many examples like nonlinear Schrödinger equation, the equation of general relativity, all these black holes and so on. So this is exactly the condition, the examples of the formation of singularity, then formation of drops, and many, many other examples. Okay. Okay, so what I wanted to describe is, I wanted to describe first theoretically how you understand the formation of the singularity for a very simple, well, for the simple model, which will be rather not very trivial, but at the same time, will contain many interesting features that will be already can be extended to this further questions about spontaneous stochasticity. So we will consider this kind of equations. So this will be our system, x dot equal fx, but with special type of the function f. So the right-hand side will be the following. It will be r alpha. R is norm of x, so distance to the origin in the power alpha. And then it will be multiplied by the function of just an angle of the spherical component of the vector. So you separate vector x into the length and direction. So the direction belongs to the sphere. So the belonging to the sphere is good because it's compact object. And what we will assume is that this capital F is a smooth function. So it's smooth function of a sphere. So the only singularity that we have here is at the origin, and this singularity at the origin will be non-Lipschitz if alpha is smaller than 1. So we are losing Lipschitz condition. And okay, so we will work with this kind of system, and this is example. This example of this kind of system. For some alpha, you can put whatever, because the form of orbits will not depend on alpha. It's just how the time is distributed along the orbits matters. Depends on alpha, but orbits will be the same. So what you can see is that everything is smooth except at the origin. So origin is a singular point, as we promised. So this is non-Lipschitz at the origin. So let's think that alpha is 1/3, as in this Kolmogorov example. And so what you can see is that all orbits, any initial condition that whenever you start on the left-hand side, any point, it will lead you to the origin. It will lead you to the origin. But it will not lead you to the origin like in usual dynamical systems. It will lead in usual dynamical system. It's typical that you are attracted at some fixed point, but this attraction always happens at infinite time. So you approach the point as time goes to infinity. So here it's different. So you will enter this point at finite time. So let's see just why it happened. So it's just this is just picture showing that this is truly the self-similar example. So you see it has exactly the same form independently of how far is it. So it is self-similar. And this self-similarity is actually very practical because essentially almost all examples most of those examples that we have in applications like nonlinear Schrödinger, Burgers equation, so they all have this kind of one kind of self-similarity, which is in partial differential equation called scaling. So some scaling invariance. So this is a ordinary differential form of scaling invariance. So it's at all vector fields is the same at all distances, only the intensity is different. Okay, so how you build up the theory for the blow-up, how you describe all these solutions, how you describe why the solution should enter the origin in finite time. So there is this very general trick. So you have to separate. What we do is, so this is, let's think about 2 dimensions. So the plane, so x1, x dot, x2. So we have x dot equal f. F is R alpha by F capital alpha. So we have this vector F, F here. So we will split into pieces. One will be radial, another will be orthogonal. So you can always split any vector into the normal and transversal part. So it will be if RF transversal. So now the specific form of the equation, this R alpha, allows us to make a derivation and to go to the new variables. So instead of distance, which was going from 0 to infinity, we will consider logarithm of the distance. And this is nice transformation because logarithm of the number which is bigger than 0 become any number. So that now is arbitrary number on the line. And then what we will do is we will introduce new time variable s as some special integral. So whenever we make this transformation, we are transforming our original system, dynamical system with singularity, to a new system which has no singularity at all. So there are 2 equations. One equation is for y, which is just direction. So y is a point on the sphere. So in here, y is a point on the circle. And it moves in time s under this vector field f transversal. So this f transversal component just shows how this point should go along the circle or along the sphere in high dimension. And then there is another variable z, which just, it's kind of slave equation. So it changes according to the change of the previous equation. So whenever you know how y is changing in time, you can substitute in another and find how z changes in time. And then you can reconstruct the original solution. So you exponent of z gives you distance. Then you see z, as you said, you just integrate the second equation. And then you also can obtain time because time can be expressed by inverting this integral. So it's also an integral. So just if you have z as function of s, integrating it, you find what is the time. So having a solution of yz as function of time, we can reconstruct distance, we can reconstruct time. And so having the new rescaled solution, we can find the old the solution in old variables. And this gives you the whole idea of how the solution is how the singular solution is obtained. Essentially, the idea is simple. So in our system, singularity is in the origin. So x should go to 0, which means that logarithm of x, which we call z, should go to -infinity, and this should happen at a finite time, so at a certain time tb. So how this relates to our new system, which we rescaled. So in the original system, as I said, so we should go to the 0 in x as time goes to finite number tb. So both x and time, they undergo finite changes. No? So the time should go to the finite number, x should go to zero. So now remember that we took x, z to be logarithm of x. So the z should go to -infinity. And also we know that the system in S variables never have any singularities. It's Ellipsis continuous, and also it's on a compact set, so it has solutions forever. So it's globally, it has a unique there exist unique global solutions in time S. So S should go to +infinity. So we have Z that must go to -infinity, and S can go to +infinity. So we have to connect this original formulation to the renormalized formulation, which is completely desingularized. So the original singular formulation to the fully desingularized renormalized formulation. And here we use this expression, and you can just simply formulate the theorem. So imagine that you have a dynamical system of Y. Since you're interested in Y dynamics at large times, it means that eventually you go to attractor. So you can assume that there is an attractor in this renormalized system. And if you have an attractor, you can also assume that there is an average of the radial part of the function on the attractor. So assume that there is average part of this function fr on the attractor. So the theorems tell that it is sufficient to have this average to be negative. If this average is negative, then the solution blows up in finite time. Okay, so the solution blows up in finite time. And why is it so? You can see just directly from this formula. So if the fr is negative on the attractor, then this integral is growing without a limit, right? So it becomes at s large positive, the integral become negative infinite, which is exactly what we need. So z goes to -infinity, which means that x, which is exponent of z, goes to 0. So at least we know that we go to the origin. At the same time, if z goes to -infinity, more or less linear, like more or less linearly as in S, like limited in a limited way, then this exponential integral converges to a finite number. And if this integral converges to the finite number, which means that S infinity corresponds to finite time TB. So the time converges to 0. So we have two systems. One is singular, another is new, which we made a trick, and it's completely regular. But whenever our new regular system goes to infinity, the original variables go to the origin, and original time goes to the finite time. So this gives you blow up. So this is exactly what happens. So what we have for our example modeling system is that whenever you start on the left-hand side, you can associate to our singular system a very simple system on a circle. So this is desingularized system on a circle. System on the circle has two attracting points, one on the left and one on the right. So this left point is interesting to us. And this left point, the average of this radial part of the function is negative. You can check this, which means that whenever solutions start on left-hand side, it corresponds to the solution on a circle which comes to this infinite point. And whenever this solution goes to this fixed point, it happens in infinite s time. But in original variables, it happens at finite t time. So whenever you come to this origin, it always happens at finite time. So you start in any point initial condition, you know at some time you will be exactly at the origin. Not close, but exactly at the origin. And there are many other situations where it happens. Certainly you can construct all these kind of examples in a different way. So for example, this colored example is that we constructed the system of free differential equations. So this is a system in a space of free differential equations, which is singular as the origin. So there is R alpha here inside, which is multiplied by some smooth function on a sphere. And again, we can have blow up, and blow up, as you see that blow up, as we just saw in the theorem, the blow up is described by the asymptotic form of the solution near the attractor. So attractor is important. So what is the attractor? So here the attractor, in this example, the attractor is so this is a dynamic on a sphere. So the attractor here is a limit cycle. So there is this periodic solution, which is an attractor. So whatever point you start, you take, you will fall into the attractor. And in the original three-dimensional space, it corresponds to the open area. So whatever initial condition you take in this open area, it will come to the origin in finite time, but it will come along this spiral motion. So, and this spiral motion is determined directly by this orbit. So you can describe what happens. But of course, this is not only what you can expect, you can also expect other attractors. So you can even form singularity in finite time by chaotic attractors. So they can be chaotic attractors, so you will come to the closer to the singularity, and as long as you come, you will kind of follow the very irregular chaotic motion coming closer to the point. So this is also possible to construct. So this is rather direct to construct it on the specific examples. And you may have question whether it really happens. So whether it makes sense for any realistic real life world. And the answer is yes. The answer is yes. And here I will give several examples. So I will give several examples, and I think that with this we stop here. So first example is analytical. So where we can really compute everything. And the reason why we compute everything here is because it's Burger's. So we come back again to the Burger's equation where everything is known. So everything is known. It's not good to say because it's not true. But at least for this equation, you have explicit solution. For this equation, there is explicit solution, at least up to the moment when the singularity occurs. And what we were talking is that after certain rescaling of the solution, you can map the dynamics, which is finite time singularity dynamics of the original system, to the system which is regular and approaches some nice attractor. And this is true. This is true. So this is true, and here I will just show you the picture which directly shows that it works. This is the same example, so it's kind of some example which is some late stages of this initial condition. So remember, it starts to becoming more and more steep and start to fall, forming the infinite derivative. So what the meaning of this rescaling is that at certain times, as time approaches the singularity, you start to look at the solution at different frames, and you scale this frame in a different way, horizontally and vertically. So every time it becomes smaller and smaller, smaller. So you kind of look closer and closer to the solution as it becomes approach singularity, but you should make it in a clever way. So you should scale in one rate. You should one type of scaling horizontally. You should in space. You should use another type of scaling in the variable u, and this also should be synchronized with time coming closer to 0. And if you do this, you will see that the solution that you observe coming closer to the singular point, they all approach this single universal red line. This is red line is universal. We know the formula, and it is exactly fixed point attractor for our system. And this can be done. Actually, this can be done explicitly, analytically. Though it's a rather formal derivation. I don't know anyone who made it rigorous just on the level of this derivation. It's just rigorous because we know exact solution. So it's, in that sense, it works. So we have this Burgers equation. This du dt plus df dx, where f is u squared over 2. In principle, you can, in Burgers equation, you also add viscosity. This we will need. But now we take viscosity to be 0. And there is this implicit solution that I was already talking about. So whenever you have initial condition, this initial condition is carried along each characteristics. So this is how the solution looks like as this initial condition. As time is growing, it becomes more and more steep until it forms this vertical derivative. Okay, we know that after this it can be continued with a shock solution, but this is, let's be careful about this. So we are not so far not going beyond this point. So also we know that as we come closer and closer to this singular point, the solution in the right coordinates is approaching this simple formula. So x equal EU minus u cube. So this is the solution that you can obtain by this rescaling. This is exactly the red curve that I was showing before. Is this graph of this of the formula, and we can in principle do something very close to what we did with the example above. Is that we take we take new time. So it was z, now it's tau. So we take time tau, which is obtained as logarithm of original time. So we should put minus in the correct way so that everything is well, nothing gives you complex number. And also x variable also should be, we change it to psi also by using logarithm. So psi is a log of minus log of x, and new time is minus log of minus time. So the two logs. And also you should just little massage u variable. So from u you go to v. And this change of variables in a very simple way, or similar way to the ordinary differential equation, gives you a new equation. So this is a new equation. This new equation, which is obtained from Burgers. So it was the Burgers. Now we have this new equation. Again, after we change this, made this change of variables, there is no, it's still autonomous equation. Coefficients do not depend on time. And we just need to find the solution of this equation. Okay. And the solution of this equation can be obtained, the asymptotic solution of this equation can be obtained from the solution that we already know. This is a solution we already know. We just substitute new variables into this solution, and this gives us the formula. And solving this formula gives us directly the asymptotic large time solutions for this system, and it will be some function which is given here function which is depends on psi minus at, where a is 3/2. So what we see is after we did this all the change, the solution in new variables is just traveling wave. It's a traveling wave. This function f is a function which goes from one constant to another constant, from 0 to 1. And it's traveling wave. We're just moving toward larger and larger psi as new time tau goes to infinity. So instead of something which in finite time creates singularity, we have something which we're used to. It's a solution which is forming traveling wave, and traveling wave propagates as long as it wants, as you look after it. So it's just traveling wave, and traveling wave goes to large psi. Large psi, as you can see, large positive psi means very small x. So something happens very, very small to the origin. And as time tau goes to infinity, you see the time goes to finite number 0. So we're starting from negative time, so we approach 0, and which means that as this traveling wave reached infinity, it's exactly the same moment as the solution of the original Burger's equation reached the singular point at finite time. So there is this connection between fixed point in the rescaled Burger's equation, which can be propagated forever, and the blow up which occurs in Burger's equation, which happens at finite time. So there is a connection, and the traveling wave solution is just describing this asymptotic form of what will be forming at that point where the Lipschitz condition will be first violated. This is our situation. Okay, and I think I actually I should not give any more analysis for today. I will give you some perspective. So where this can be important, where this kind of the idea is okay, why we should care about singularities in differential equations, both in ordinary differential equations and in partial differential equation, which is a blow-up. So in ordinary differential equations, I already mentioned you one example, n-body system, but n-body system doesn't have any peculiar properties like spontaneous stochasticity and so on that I'm going to discuss about later next time. Just it does have non-Lipschitz. It does violate Lipschitz condition. It does create a lot of problems, and many of these questions are already understood. But it does not lead to the situations that I'm going to talk. Is that spontaneous emergence of the probability? So the emergence of probability from something which is completely formulated completely deterministically, like that's what Lorenz said. So we need more singularities. So where these other singularities appear, and in fact, I will be showing you some singularities, which I already showed you singularities which connected to the fixed point attractor, which is Burger's equation, and Burger's equation is a prototype for many other equations where something similar occurs. For example, compressible hydrodynamics, for example. And also there we know that nothing probabilistic happens after, because there is a shock wave. It's continued by the shock wave. So I'm going to show you some examples which is connected to the real world systems, where we can expect something very peculiar after the singularity occurs. So one is this video. I think this is activity. This is an area of research which is also carried out. This kind of research also carried out in our laboratory by Andrei Nachbin and also his students. So this is about a drop. So when you this is what you will see when you take a drop and throw it on the surface of the water. So what you think is that drop just enters and disappears. So it's not what happens. Actually, what happens is, well, it certainly would be finite time blow up because there is a drop. Then at the moment it touches the surface of the water, there should be some singularity appearing between the surfaces of the two liquids. So there should be some singularity appearing at the moment of the contact, but actually what happens is way more complicated. So let's see what happens.
They keep going. We've seen as many as 7 such events in a coalescence cascade.
So let's see it several times. So what you will see is that the drops enters the water, it emerges in another drop, smaller. And this drop falls, emerges another drop smaller. This falls, emerges another drop smaller. And so this...
They keep going. We've seen as many as 7 such events in a coalescence cascade.
You see? And it's only because the liquid is real, so there is a question of viscosity. So it's viscous, and there is viscosity. There are dissipative processes in various outside. So the system is not ideal, is because it ends. But in fact, in ideal situation, when you have ideal liquid, it will happen forever. So there will be not 1, 2, 3, 4 drops emerging. There will be infinitely many. Every time it will be smaller. And what is expected? So the time of the jump that every drop will leave will decrease as a geometric progression. So like first drop jump during like 1 second, next half a second, then a quarter second, eighths of a second, and so on, which means that despite there's infinitely many events happen in this interval, the time when it ends is finite. So in a finite time, everything will end. And this is a kind of an example of the blow up, which occurs similarly and periodically. So this is this kind of the example which analogous to this periodic attractor of this regularized system that I was showing you in a specific orbital divergence equation. But here you can see it in the real.
They keep going. We've seen as many as 7 such events in a coalescence cascade.
Well, I think you can see it forever.
They keep going. We've seen as many as 7 such events in a coalescence cascade. They keep going. We've seen as many as 7 such events in a coalescence cascade.
If you look for it in YouTube, you will see the whole. I think I clipped it from some of the popular scientific programs in YouTube. Okay, so this is one of the solutions, and this is correspond to periodic blow formation of singularity. The second example is about formation of the singularity in the incompressible ideal fluid dynamics. So you have incompressible ideal fluid in 3 dimensions, so it moves. And you start with smooth flow, which is initially smooth. Then we know that if we start with a smooth flow, it will continue to be smooth. But then it starts to become more and more complicated every time. And there is a big open question, which is still open, is whether the solution exists forever or not. So like in Bürger's equation, it will not exist forever, so it forms singularity. Whether incompressible Euler equation will have a solution that is exists forever, in time forever. And this is kind of the older brother of this famous millennium problem, because millennium problem is kind of opposite question. It's a question whether, well, it's the same question, but with this answer which is kind of opposite, which is anticipated. So in the millennium problem, which is one of these 7 famous problems that we have to solve. The question is whether the solution of the smooth solution of the Navier-Stokes equation exists forever, whether it doesn't. So, and essentially, the question is rather inviting to prove that whether you have a smooth regular initial condition, the solution exists forever. So for the Euler equations are much older than Navier-Stokes equation, and it's exactly the Navier-Stokes equation without single term. So Euler equations, they have more or less 300 years, and these are equations where you remove the viscous term, and the same question is valid for the Euler equation. We don't know whether the solution exists forever, and the solution, or the answer anticipated is no. It looks like similar to the Burgers equation. It creates singularity in finite time, but nobody can even see it. So the numerical simulation actually essentially do not give any clue what really happens, because it even numerically is an incredibly complicated problem. And this example, which we show here, is quite a recent solution of Ciro Campolin and myself. So he's our student from our lab. And this is the study of the Euler equation just in a different space. So we're considering Euler equation in what's called logarithmic lattice. And the solution that you see is exactly the mapping of the original Euler equation to this rescaled system where we can associate blow up to the attractor. And we just can see how it works. So we put initial condition, smooth initial condition, and it moves. So it develops in time. We know it can develop in time forever. And it developed a wave, like you see in Burgers equation, we already had a wave. So we showed that the formation singularity can be mapped to the wave, but this was a traveling wave. So it was a wave which does not change its shape. So here the wave actually does change its shape all the time. And in fact, it's a chaotic wave. We can even compute Lyapunov exponents. It's positive. So it's something which moves as a wave, but it's always moves. So the wave just oscillates, and it oscillates chaotically inside. So internal motion is chaotic, but at the same time, it moves with a finite speed. And the fact that it moves in this form, so just assuming that it moves in this form, is identical to proving. So if you is identical to saying that original Euler equation blows up in finite time, because the moment this wave goes to infinity, the solution in original equations becomes singular, and time in the original equation goes to some finite number. So this is another example, and then I can show that this is very simple and almost a philosophical example. The third one. Yep. So this is a Bilinski Kalatnikov Lipschitz singularity, which is known quite a long time ago. Surprisingly, how they discovered it. So much time before the chaos was even appeared. So it's beginning of 60s. And it has to do with equations of the Einstein equation of general relativity. So remember that Einstein equation of the general relativity, they're very complicated. Very complicated, but you can have some special solutions. So the simplest special solution is if you take everything spherically symmetric. So everything is the same in all directions. So that's what you see. You kind of it doesn't look to be that everything is the same in all directions, but you can look for such a solution, and it gives you the very well known the solution for the universe, which either collapse or expands, or it can expand and then collapse. So the universe can start at a certain moment. This is what we know, Big Bang. So it's from a point, then it expands, and then it collapses back. Boom. So, and this is a property of this spherically symmetric solution. but universe doesn't have to be spherically symmetric. So the isotropic, let's say, better to say not spherical, isotropic, because it's space-time symmetric. So isotropic, it doesn't have to be isotropic. So the Bilinski-Kalatnikov singularity is a solution already for the case where you assume that it's still homogeneous. So universe is everywhere the same, but not isotropic. So it's different, has different properties in different directions. And then you can just write equations of motion and solve it. So again, what you can see is the formation of a singularity. So it's kind of what we describe as a blow up is when universe ends. So imagine, so now we had some, I don't remember how many billions years after the Big Bang. So universe expanded. So we are here now, and then it will collapse, right, to the point. So at the moment it will start to collapse. The question how it will collapse. It should collapse in finite time as well. So it's singularity of the equations. And what they did is that they made a mapping very similar to what I was describing, and which maps the singularity to something which is just normal dynamical system. And this dynamical system behaves as you can see.
It keeps going. We've seen as many as 7 such.
Not this picture. So this is a picture of how universe changes, kind of subtracting the size. So actually it's just the shape which is shown. Yeah, but size always coming to zero. So universe collapses, but as it collapses, it faster and faster makes this motion, and these are completely chaotic motion. So as our uniform comes to it, it comes chaotically and creates a singularity. So this is an example of the chaotic singularity. So singularities which lead to the violation of the Ellipsis condition, they're actually everywhere around us, and they're important. So the question that we're going to address on the next lecture, what next? So formed singularity, what is after? So what is after, in a very simple example that we started, it tells that after you may have solutions, but solution is not unique. So you have to think what solution you should follow. One of them, so if it's one of them, choose which one. And this choice is very clear, for example, for the Burger's equation. You choose a shock solution. So there is infinitely many solutions, in fact, but we choose a shock solution and continue solution with a shock. Or they can be, or you don't need necessarily choose, or maybe you need to use a different system. You cannot choose any solutions, and then maybe your universe ended, or maybe universe didn't end, and some new universe appears. So this is why it's quite philosophical. Or it does not necessary that you choose one of the solutions. It may be you choose some of them or all of them, but with different probability. And this is what spontaneous stochasticity means, is that there is a way which is rigorous and very robust, such that in some situation you can prove that the system cannot choose one solution. In fact, it must choose a subset of the solution, sometimes infinite subset of the solutions, assigning probability to each of the solutions. So after you pass for singularity, spontaneously you should continue with the probability along different solutions. So this is what we're going to discuss next, to see how this at all can happen in differential equations. So differential equation, which we formulate formally deterministic way, as Lorenz wanted, but after a certain moment of time, we must continue the solution probabilistically. And probability is already well defined by the original deterministic equation. So that's it for today, I think. So I hope something was clear. So I go to the last page. No? Thank you. And how much time? Oh, just 1 hour and a half, more than so thank you very much.
Okay.